All right. Thank you all for coming. I hope that you brought some enthusiasm with you from the beach, since today we are going to talk about team building organizations by the river. Actually not. I'm going to talk about building a highly scalable and fault-tolerant event store. A few words about myself. My name is Milan Savic. I work as software engineer at Axonic for a bit over a year now, as one of contributors to Axon Framework, but I work on Axon Server as well. I introduced a bit myself, and I would like to get to know something about you. So if you would like to go to www.menti.com on your phones, on your laptops, whatever you have in your hands, and use code 620344, you're going to be prompted with this question: do you know Axon Framework? And I would really like to get a feeling how familiar with the framework you are. I hope that internet, gods of internet are going to work for us today. All right, it's working. Give you a few more moments. Okay, so I guess that I'll have to introduce the framework itself. So Axon Framework is free and open source Java framework that is used by applications that want to make the most out of concepts like domain-driven design, command query responsibility segregation, and event sourcing. On this slide here, let me now just grab the laser pointer. We can see an architectural overview of one typical Axon application. On left side, we have a user interface, and we have a user that wants to do something with our system. In order to do so, one would issue a command. A command represents an intent to change something within our system. It is basically a message. That message will be dispatched on the command bus to command handling components. Usually, those components are our aggregates from our domain model. Those aggregates know how to validate the command and how to execute it. So that's the thing that they are going to do. They will execute the command, and as a result of that command execution, we will have some events triggered in our system. Event, that's the second type of message that is supported by Axon, and it represents a fact that something had happened in our system. Two things happen with the event. The first one, that it gets persisted to the event storage. And later on, we are going to use those events to source the current state of our aggregates. The other thing is that it gets published on the event bus. And we use buses in Axon Framework quite a lot. It helps us to achieve location transparency. So the sender of the message does not have to know where the recipient is. On the other side of event bus, we have event handling components. They are reacting to those events, and they are transforming those events to updates of view models. Here's where CQRS concepts kick in, so we can have several views of the same event stream based on the same events, actually. We almost completed the circle. The third message that Axon supports is the query message. It represents request for the information. So when user wants to find out about results of previously sent command, one would issue a query to a query bus, and it will get the current state of view models. This is all nice when we are speaking in terms of single JVM. However, if we want to distribute our application, so if you want to have more than one Axon Framework application in our system, we need some infrastructural component to tie all those applications together. At Axonic, we are also building Axon Server, which is basically used to route all these three types of messages through our system, but it is also used to store those events. Oops, sorry. to store those events in the event store. It comes in two flavors. The first one is Standard Edition, which is free and soon to be open sourced. And the second one is Enterprise Edition, which has a little bit more features. One of those is clustering, which we are going to talk in more details today. Event store used to store events, and those events are consumed by components that publish them, but also by components that are interested in handling them. What is characteristical about the event store is that it is append only, so its state only grows during the time. It supports also reading of those events. You can read those events by aggregate identifier, or you can read those events from a certain point in time to a certain point in time. Okay, so this is all good when we are speaking about a single instance of Axon Server. However, the problem that may occur with having only one instance is that we are going to have a single point of failure in our system. What we want to do is to have a cluster of Axon servers in our system, so more instances of Axon Server. That is much easier said than done. Now we are in a full distributed system, and we have to take care of consistency. So how in the world are we going to take care of storing events when Axon Framework sends us a batch of events to one Axon Server node, that this information is replicated to all servers in a node, and that if that server fails, other servers can pick the work up. This is what distributed consensus protocols are dealing with. So they are taking care of having the same information, basically having consistency within our cluster. On this slide, we see one typical system of such. On the left side, we have clients that are, in our case, usually Axon Framework applications, and they are sending batch of events to the Axon server. Servers contain consensus module, which is responsible for appending entries to its consensus log. Now you may see the resemblance between the consensus log and the event store. The secret is that we use the same technology for storing consensus log and event store, storing events in the event store. The other responsibility of consensus module is to successfully and safely replicate those log entries to the instances of other servers in a cluster. Third component in this system is a state machine. In our case, that's the actual event store, and it will take log entries from the event log and apply them to itself. There are several protocols that are dealing with these kinds of problems. You may have heard of Paxos, Zab, Raft. However, you may invent your own protocol, which is something that I would highly discourage of doing because it is not that trivial to be done. And you have to at least prove to yourself that it's going to work in all corner cases. So why bother when there is something which is already working properly? Okay, so we opted for Raft in Axon Server. Raft was basically a PhD thesis by a guy called Diego Ongaro in August 2014. That's the time when it was published. It was built as a response to Paxos algorithm, which was by that time basically the synonym for distributed consensus. It is built with a rather strange drive, and that is to be more understandable than Raft. They used one simple technique to achieve understandability, and that's the problem decomposition. They decomposed the problem of distributed consensus to several sub-problems, such as leader election, log replication, snapshot installation, cluster memberships changes, and such. And they would attack those problems individually, and they were always driven by understandability to solve each of those problems separately. Okay. Let's take a peek under the hood, so how it is actually working. A Raft server can appear in one of three states. It can be in follower, candidate, or leader state. When a node is started up, it is started up in follower state. Leader of the cluster uses heartbeats to inform followers that it is still alive and that the cluster is functioning properly. Followers have timeout, which is called, we'll later see, election timeout. And if the follower does not hear from the leader within that timeout, it will move to candidate state. So it will try to candidate itself to become the new leader of the cluster. In candidate state, basically what we are doing, we are requesting from other nodes in our cluster to vote for us, to support us in candidation for leadership. There are three possible cases that can occur here. We can either receive majority of votes, that means number of servers in a cluster divided by 2, and we add 1 to that. So in a cluster of 1, majority is 1, in cluster of 2, majority is 2, in cluster of 3, majority is 2, and so on. So you may figure out that having odd numbers of servers in our cluster basically gives us the best ratio of cluster size and cluster availability. Whenever the majority of nodes are up, our cluster is available. Okay. The other thing that can happen that is when we are candidating is that there is a new leader. So there was some other server that was candidating itself for leadership, and that guy won. It has a term which is greater than ours, and we just move to follower state. Or we can split vote with other member of a cluster, and then we run elections again. All right? When we are in leader state, the only thing that would cause us to move to follower state is that there is a new emerging leader. So there was a leader election, and there is a new leader, so we will just move to that state. I was talking a bit about terms. Time in Raft is divided in terms. Each term starts with an election, and that election can be either successful. It is successful when we have a leader as a result of leader election, or in case here for term 3, can be unsuccessful, which means that we need to run election again. While our cluster is doing elections, it is unavailable, so we as implementers tend to limit the number of elections that we are going to have in our system, but also the duration of those elections. Let's take a look how leader election works now. I was talking about election timeout. There are actually two values in Raft. It's minimum election timeout and maximum election timeout. Our actual election timeout is a randomized value between those two values. In Axon Server, based on our experience, we came to values of 1 second and 2 seconds for minimum and maximum election timeout. Those are fixed. And based on our experience between those values, our cluster behaves the most stable. Okay, so we didn't hear from a leader within that timeout. Then we are becoming a candidate. We are going to increase our term and vote for ourselves. The other thing that we are doing is using a message which is called request vote, and we are going to send that message to other nodes in a cluster. If we receive majority of votes, we are going to become a leader. Or if we hear from a new leader, we are going to step down, become a follower. The third possibility is to have a split vote situation. Then we run elections again. Now you may think of what will prevent us to have several split vote situations in a row, which would make our cluster unavailable. Basically, theoretically, nothing, but there is a discussion in the paper which, if you're interested, can read, and I would recommend to read it, stating that practically, if your random algorithm is good enough, having 2 or even 3 split vote situations in a row is practically impossible. Okay, so we saw elections from eyes of a candidate. Now, if we are a voter, the rule for voters is that they are not going to vote more than for one leader in given term. This information is persistent, so if that voter restarts itself for some reasons, it will preserve that information and it will avoid voting for another candidate in that term. We said that we need majority of votes to win and that each voter can vote at most once. When you combine those 2 rules together, that means that we cannot have more than 1 leader per term. Okay? Let's take a look now at this simulation of a leader election. Here we have 5 servers, S1 to S5, and they all have their randomized timeouts. In this case, we may see that probably S3 is going to be the first one that is going to time out. So it is going to send request vote RPCs to other servers in a cluster. And if it receives majority of votes, it is going to become a new leader. Here, we see that all other nodes granted their votes to it. So now it is a leader. It became here in bold. So that's how a leader election works. Great. We have a leader now. We can now start serving client requests. When Axon application generates some events, it is going to send those events to the current leader of the cluster. That leader would append those events to its log, and leaders always append events, always append log entries. They never muted them or they never delete them from its log. However, followers may do so. Let's take a look at the structure of Raft log. Here we have log index from 1 to 8, and we have log entries which happened in specific term. In term 1, we have 3 log entries. In term 2, we have 1, and in term 3, we have 4 log entries. We appended new events to our log entry, so we are going to try to replicate those events to other nodes in a cluster. For that, we are using append entries RPC, which will contain the current term and current index of that log entry that we want to replicate as that entry itself. Similarly to leader election, when we receive majority of responses stating OK, we managed to replicate that information to our logs. We are going to state that this entry is committed. This is a really important point in time in Raft saying that something is committed. At this point, we can guarantee to our clients that whenever cluster is up, that information is going to be present in all leaders' log. So that information will never be lost. So we have this specific commit index. And in this case, we can see that commit index is 7. Why is that? Because first, third, and fifth server have successfully replicated that information to their logs. Okay. Append entries can also be used as heartbeat. So if you don't have any entries to send to other nodes in a cluster, we will just send an empty append entries. And it is really important that this heartbeat is sent regularly in order to prevent unnecessary elections and unnecessary unavailability of cluster. In Axon Server, we are using gRPC for inter-cluster communication. that gives us a lot of benefits such as flow control and bidirectional streams. So we can send several append entries and receive only one response per client, right? The thing that is really important also to underline here is that you do not, for example, you can see this fourth server, and it does not have that many entries. If a leader focuses his attention to trying to update its log, it may forget to send heartbeats to other servers in a cluster, and that's what we want to prevent. So we need to find the balance, right balance there. Okay, let's now take a look at the log replication, how it works in practice. Here we have leader S5. We are going to request some information from it. Here first we will see some heartbeats sent to other. We are going to request new information. We see in term 2 we have a new information to replicate. It will be replicated to other logs, and now we are receiving OK responses for append entries message. Once we have majority of votes, we can consider this entry committed on the leader. And with the next heartbeat, we are going to send that commit entry. That means that at this point, all other servers can apply that entry to their state machines, in our case, to their event stores. So those events will be appended to each Axon Server event store in a cluster. All right. How do you feel about this? Is it, I'm going too fast, too slow? Can you follow? Okay, good. I stated some rules. However, those rules do not guarantee us any safety. There are 5 safety rules proposed by Raft, and we are going to walk through those here quickly. The first one is election safety. I already mentioned this one. If we have a rule that majority of votes are required for a candidate to become a leader, and if a follower can vote at most once, we cannot have more than one leader in our cluster. There is specific restriction on granting votes from voters, and that is the situation. Think of the case where you have a fresh node joining the cluster. For some reason, it is in partition network and it does not hear from the leader. So that one would time out and would request votes from other servers in a cluster. It can happen that if you don't have any restrictions, that it can receive majority of votes, meaning that it has to replicate its log, which is empty in that case, and we will lose all the data in our cluster. So this is not good. We add addition to request vote message, and that is the current term and the current log index of that candidate. So if I'm a follower, I will not give you my vote if I have more entries in my log. It does not make sense, right? So only candidates that have the most up-to-date logs can win. Second safety mechanism is leader append only. Leaders always add log entries to their logs. Okay. There is a really important rule, which I do not have time to explain now, but we can discuss afterwards if you're interested. And that basically states that when you're elected as a new leader, you must not commit log entries from previous terms, even though you were the leader of those terms. So it is not possible. The only way how you can commit those entries is by committing an entry from your term. The small addition to the protocol that we added is having a specific log entry, which basically says, okay, I'm the new leader. Whenever leader is elected, it will try to commit that entry. If it commits, then all previous log entries are committed automatically. That basically a little bit speeds up the process of committing previous entries. We don't have to wait for next client request to be sent to us. Log matching. If two logs contain an entry with the same index and term, then the logs are identical in all entries up through the given index. Based on append entries message, as we saw currently, this is not possible. But if we add a small consistency check in our append entries message, it is going to be possible, and that is to send a previous log index and previous term of the entry that we want to replicate. If the follower does not contain the log entry at that position, it will respond false to us, and it will respond false until these indices, these log entries match. From that point on, leader can start replicating its log, and it will overwrite, maybe overwrite all log entries from that point in the follower. Leader completeness, a little bit difficult to prove, but I'll try. I'll do my best. If a log entry is committed in a given term, then that entry will be present in the logs of the leaders for all higher numbered terms. Pretty strong guarantee. That means that there will be no leader that does not contain all committed log entries. Let's try to prove the other way around and see that it is not possible. In this case, we have server S1, and it committed an entry. Server S4 and S5 do not contain that entry in their logs. For some reason, S1 can go down. That means that any of these four servers can candidate themselves for being a new leader of the cluster. Let's say that for this discussion, S5 candidates itself. S5 can receive a granted vote from S4, but in order to win the elections, it needs one other vote from S2 or S3. Let's say that S3 grants its vote. That means that we do not have leader completeness property. However, this is not possible. If you remember election safety, we are not allowed to grant vote if the candidate does not have the log as long as ours. So this is not a possible case. Hence, all leaders must have all committed entries in their logs. The last one, basically the most important one, is state machine safety, and it says if I apply some entry at given position, there will be no other server in the cluster that can apply a different entry. It is basically a result of two rules, the leader completeness, and if we said that we as followers cannot apply anything else that it is not in the leader's log. Those were some basics of Raft. Hope that you understood at least part of it. Let's now move on and see how are we going to deal with the fact that our Raft log is increasing only. From time to time, we are going to go to each servers. Basically, each server will take care of its log compaction. In Axon Server, on each hour, we are going to clear all logs that are older than 1 hour. Hence, we are going to save some disk space. Regarding the snapshotting, it is pretty easy for us because our event store already contains all the snapshots because it is immutable and it grows only. Now we can have a follower that is really slow and that its last index in its log is not present in the leader's log. In that case, we are going to start install snapshot procedure. It's really important that this install snapshot procedure is idempotent, which is in our case by design. And it is really important to send hard bits during install snapshots because our snapshots are usually enormous and can take a lot of while. So we cannot install a snapshot within one message. We have to send several messages to install snapshot. One addition that we added to the append entries response message is the last event sequence in our event store. So when we cannot apply, when we cannot append the entry to our log, we will send the last applied event sequence from the event store to the leader. So leader will open a stream. For internal implementation, we're using Project Reactor. It gives us a great flexibility to batch our snapshot chunks however we want. It will open the stream from that point to the current point in time, and it will start sending snapshot chunks to the follower. If that leader fails, the new leader will continue this process, and the good thing is that we already applied some of the events to the follower. Our last event sequence is going to be changed, and the new leader will continue where the previous one left off. Okay. Let's see now how we can change our cluster configuration. We opted for an easier solution. There is a more complicated but more powerful solution proposed by Raft. So basically, you can have arbitrary changes within your configuration, but it requires you to keep track of majorities from old configuration and majorities for new configuration. However, we didn't find the justification in our business case to do so. So we opted for an easier path. We opted for 2 operations, and you can do those 2 operations only one at a time. You can either add node or remove node. Removal of node is not that difficult. We need to first inform it that it's going to be removed. So when it is removed, it cannot start acting crazy and timing out, starting elections, things like that. And the other thing is just remove it. Cluster configuration log entry is somewhat specific because it is applied not when it is committed, but the first time the follower gets it. So it does not care whether it's committed or not. Add node, in our case, is somewhat more complicated because our state is really enormous. And think of the case where you have one node cluster. You want to add a new node, which is completely fresh, and I don't know, maybe the first node is running for a year. It has billions of events. If you try to add the fresh node right away to the cluster, before installing a snapshot, we're going to change our majority, and we are going to cause our cluster to become unavailable until the install snapshot on the fresh node is not done. So what we do, we first install snapshot, and then we add it to the cluster. Installing a snapshot can take quite a big amount of time, as I said. So we want to detect that. We want to be sure that we do not want to add slow followers to the cluster. How are we going to do that? We are going to use a round mechanism. When a new node joins the cluster, it will start installing snapshot from the 0 event to the current event that is present in the leader. And we will measure that time required. If that time is larger than minimum election timeout, we are going to start round 2, and we are going to start round 3 until this, the time required for installing a snapshot is smaller than minimum election timeout. Otherwise, if we reach maximum number of rounds, which in our case, for example, 10, then we are just going to proclaim that this node is just way too slow and we cannot add it to the cluster. The problem with the Raft is somewhat of performance bottleneck because all operations go through leader. Having a large system will basically slow our cluster. Fortunately, within the Axon framework, we already have a natural division. We divide our Axon applications in contexts. Those are bounded contexts if you're familiar with DDD principles. And here on this image, we can see that we are going to have a Raft group per our bounded context. And we are going to have a leader and that leader can be a completely different server. On this slide, we see that server 1 is leader for context 1, 3, and default. Server 2 is leader of context 2. That's how we spread a load a bit. There is one specific context that is called admin context, and it is used for internal Axon Server purposes. It is used for managing the topology of our whole cluster, of our whole system. It knows about each and every node in our cluster, about context, and which node is the leader of which context. When we want to add a new node to the cluster, we'll contact the leader of admin group, and the leader of admin group will contact the leader of corresponding context, and that's basically where the client request ends. Testing, pretty important ingredient. Those are all types of tests that we do and all environments that we run on. I want to just say that we tried to abstract all the environments that we are running on. So our tests are written in JUnit Cucumber. We also have some performance tests. But if you want to run those on Docker Compose, Kubernetes, virtual machines, Azure, AWS, Google Cloud, it's just a matter of configuration. So on your build environment, but also on your local environment, you can run your tests against all those supported environments. Chaos experiments is something that we do from time to time. We just gather together and try to slow down the network, drop packets, and just pick the Axon server and see how it's going to behave. Then we analyze logs and see whether it behaved properly or not. The most important slide, I'd say, this is something that you can take with you. What we learned while we were implementing Raft in Axon Server. So start as simple as possible. In our case, we debated a lot whether we want to support arbitrary cluster membership changes. We opted not to do it because we couldn't find the business value in it. There are also some debates whether we want to do pre-voting. Pre-voting is basically a mechanism to see, before requesting a vote, whether you will have a majority of votes, majority of nodes voting for you. We also didn't do it because we didn't find a justification for it. The most important one is do not deviate from the Raft paper. If you start inventing your own rules, if you start cutting corners, and probably you're going to be tempted while implementing Raft, please don't do it because you're opening a Pandora's box and who knows what corner cases you just introduced. Timing is really, really important. Figuring out your minimum election timeouts, figuring out your heartbeat rate is pretty important because it is affecting your cluster availability. I already talked about this. Large state makes install snapshot more difficult. If you need to achieve consensus in your system that has a large state, pay special attention to it. And the last one is test everything. So try to automate as much as possible, try to see all corner cases, and yeah, just try to cover as much as possible. Here are some resources that I want to share with you. You can find them in slides, which I'm going to share later on. If you're interested in how event storage is actually working under the hood, we have a webinar next Tuesday or Thursday, I'm not sure. You can check it on this link. It's going to be held by our CTO, Allard Beiser. And yeah, that's it. Thank you. If you want, you can visit again www.menti.com, use the code 620344, and just leave me a feedback whether you found this presentation useful or not.
Thank you so much. Is there any question? Okay, we have a question. It seems that Axon has his own Raft implementation. why didn't you delegate on databases that already provide consensus?
Databases already provide consensus. Well, basically we are a database, right? So we built an event store in order to overcome, because for the event sourcing, the most important thing is to have your order of events, right? Those guarantees can be only guaranteed by relational databases, but they have problem with horizontal scalability. That's the reason why we started building our own purposefully built event store. So we are appending only events, and we are only reading. So that's pretty simplified database, but it is really highly, it hits the point, right? It does not do anything else.
Yeah. Okay, thank you.
Right?
Any
Thank you, guys.
question? No? Thank you so much for the talk.